Hello, my name is Chris Brinton. I'm a second-year PhD student in the Edge Lab here at Princeton. Over the next few minutes, I'd like to talk to you about a research project going on in our lab, robust visualization and recommendation techniques for the emerging era of education. MOOCs, short for Massive Open Online Courses, have become quite a viral phenomenon over the past few years. For instance, there are currently over a dozen platforms, like Udacity and EDX, which launched in late 2011, and Coursera, which launched in early 2012. Let's take a look at some of the features that are common among these MOOCs. They're all online, free, and offer open content to anybody who wants it. They all have discussion forums where users can post and answer each other's questions and socialize. And they all have a massive number of enrolled students. For instance, a course we had on Coursera had over 50,000. But there's still room for improvement. For one, there's a very low completion rate, meaning that the majority of students who start these courses don't end up finishing them. Additionally, MOOCs have become an ideal setting to apply learning theory techniques for the enhancement of the student experience. Motivated by this previous statement, the research thrust in this project can be described as follows. We want to develop methods to improve the experience of students, as well as instructors, on OpenCourseWare. Now, this is a very broad topic that has many dimensions. We will focus on two of them here. First, we want to develop a tool to be able to graphically visualize the dynamics of the discussion forums over time. And second, we want to use such visualizations to be able to make effective recommendations of learning partners to students. As we said, there are many more, like personalizing learning experience to each student. We will not go into those here. First, let's talk about visualization. In order to visualize the learning process, we need a method that can extract the key concepts from the discussion forums. We've developed an algorithm that can extract the key, important words from the threads. Once we've obtained these concepts, we can link the students to them based upon their posting history. If there's a concept called power control, and you've commented on a thread containing the phrase power control, then we would establish a link between you and that concept. When we apply this strategy to our Coursera course, we get the graph shown at the left. The red nodes denote the users, and the blue are the concepts they created. This graph is shown in a concise and radial structure that can help us determine which users are connected to similar concepts. In order to make recommendations, we have to look at the graphical structure in some more detail. First, we assume that the graph is directed. In this case, an edge indicates a causality relationship. This means that if A points to B, then A depends upon B for its existence in the graph. We assume that upvotes become the weights of the edges because they denote connection strength. In this simple example, we throw 3 users and 3 concepts in a thread. User 1 started the thread, and as such, C1 points to him. Users 2 and users 3, on the other hand, posted on something containing C2 and C3 respectively, so they each point to those respective comments. The physical meaning of a link in this sense is a post, so we take as that link's weight the number of votes that the post has received. When looking for similarity between 2 users, we want to see 2 things. First is a small number of hops. This means that we don't stray too far on the path between the 2 users. Second is high weights in between the 2, which means that we're traversing important posts when we're going between the 2 users. If we satisfy these 2 properties, then that means that we have a good pair. But there's one problem that prevents this method from being robust. We don't know the weights between the concepts themselves, because the concepts cannot actually vote on each other. In order to deal with this computational issue, we found it convenient to represent our graph in terms of an electrical circuit. Each element in the circuit has some physical meaning to the original graph. For instance, we can look at user 1, who created the thread in the first place, as the source of the information, and therefore he becomes the energy source of the circuit. The concepts become the junction points between these conductance values, and the conductors are the edge weights. It turns out that if we make one assumption about the current flow in the circuit, then we can use elementary circuit theory to find the missing values of the conductances between C1 and C2, and C1 and C3, and then transform them back into the original graph. Goals in this research can be summarized in 4 main statements. First, we want to develop methods to visualize learning graphically by relying on user-concept relationships in our keyword algorithms to extract key concepts from text. Second, we want to devise robust algorithms to make effective learning partnership recommendations for students. Third, we would like to integrate our solution into our own online platform, 3 Nights and Done, and solicit student and instructor feedback on its effectiveness. And fourth, we'd like to incentivize collaboration with other online platforms. Thank you for listening. If you have any questions, please feel free to contact me. My email address is cbrinton@princeton.edu.